Alrighty guys, let's go ahead and get started with these rotational notes. And right now we're going to intro what rotation is. We're going to start off by talking about the variables of rotation. The first variable we're going to talk about is angular position, also known as theta. So you guys see this symbol right here. That just means theta. And we're going to say that theta is talking about the rotational location of an object. So these objects are circular, and its theta is representing that location on that object while it is rolling around. The units for theta are going to be radians, and 2 pi radians are equal to 360 degrees, which just equals 1 complete rotation. So this might sound familiar for some of you guys from what you've learned in your math class about radians and degrees and the relationship. Next, we're going to talk about angular displacement, and displacement is really just saying the change in position. So we remember that this little triangle right here means delta, so delta theta is angular displacement. And like we said before, the change in position is really just our final position minus our initial position. Nothing new here. The slope of a theta versus time graph is going to give us a new symbol, which is omega. And some of you guys might be thinking, well, if theta means position, that's basically the slope of a position versus time graph, which I recall to just be velocity. And yeah, omega is velocity, but omega is the angular velocity. Again, this symbol right here is just an omega, and that's just equal to the change in theta over the change in time. In other words, the slope of a theta versus time graph. So the angular velocity is just the rate at which the object is spinning. So think of it as how fast is this object spinning around. The units are going to be radians over seconds because we can find it by taking the slope of a position versus time graph, and the slope of those two quantities would give us radians per second. So now some of you guys might be noticing a trend. So the slope of an omega versus time graph is going to give us alpha. And if we think about this in terms of regular kinematics, the slope of a velocity versus time graph used to give us acceleration. Direction is usually said to be clockwise or counterclockwise when talking about rotational velocity. Angular acceleration is alpha. So this symbol right here is just called alpha. And alpha is just the change in omega over the change in time, which is just a fancy way of saying the slope of an omega versus time graph. Angular acceleration just means the change in the rate of spin. So how quickly are we changing the rate at which our object is spinning? And the units are going to be radians per second squared. So like I hinted on the last slide, some of this stuff sounds oddly familiar. So I'm going to go ahead and show side by side the 1D translational variables that we're used to versus the rotational variables that we just started learning about. So displacement in 1D, we're familiar with just being d or delta x, and in rotational motion, it would just be theta or delta theta. Velocity is represented as v for our old symbols, and with rotational, it's going to be represented by omega. Acceleration is represented by the letter a with translational, and then in rotational, it is represented by the letter alpha. So now that we have those variables underway, let's take a look at the equations that we might use for rotational kinematics. So the first equation, some of you guys recognize it, it's a little pup. We have Vf equals Vo plus A times T, and in rotational, we have omega equals omega O plus alpha times T. This is the exact same equation. All we do is just swap out the variables. Take a look at our next one here, and this is really our big dog equation, just moved around a little bit, where delta x is equal to initial velocity times time plus 1/2 at squared. With rotational, it would be delta theta equals omega initial times t plus 1/2 alpha t squared. Exact same equation, just swapping out the variables. And lastly, we got shaggy cat, which is just Vf squared equals V naught squared plus 2a times delta x. In rotational, it's the exact same thing. We just use different variables. Omega squared plus omega naught squared plus 2 alpha times delta theta. Some of this is going to seem kind of new to you, but some of it should seem a little old. And really what we're doing here is we're exploring similar problems than what we did in 1D and 2D kinematics, but we're doing it in the rotational plane now. So let's take a look at our first example problem. We're going to say that we have a sphere which is initially rolling at 15 radians per second, and the sphere comes to a stop after 20 seconds. We want to figure out what the rotational acceleration is, as well as how many rotations the sphere has made. So if you recall, our first step when solving problems is to list our variables. So I'm going to go ahead and start listing them. So the initial theta, or the initial rotational location of the object, is 0 radians. And this will be the case most of the time, because we can assume that the object is just starting at 0 degrees. Our final theta is unknown because we don't know when this object stops, what angle it has stopped at. Our initial omega is going to be 15 radians per second because that's the initial rotational speed, which is given to us in the problem. Next, we have our final omega, which is 0 radians per second, and that's because it tells us that it comes to a stop, meaning that it's no longer moving. If it's not moving, it has no angular velocity. So the alpha, or the angular acceleration, is unknown because that's what it's asking us to solve for. And lastly, the time has been given to us in the problem. It's just 20 seconds. So now that we have all of our variables listed, we would do exactly what we would do with normal kinematics. We would now look for an equation that's only missing one of the variables that we are missing, and then use that to solve. So if I look at my equations, I can see that little pup is what we're going to need because I have both of my omegas. I also have time, but I'm just missing alpha. So if I plug in my numbers to my equation, I get 0 equals 15 plus alpha times t. I rearrange it. I get alpha times 20 is equal to negative 15. Solve for alpha, and you find out that the angular acceleration should be negative 0.75 radians per second squared. We know our angular acceleration should be negative because our object is slowing down. Now that we have the angular acceleration, we can solve for theta final. We have two options on which equation we can use, but I'm going to go ahead and use big dog. So I have theta final is equal to theta initial plus omega initial times t plus 0.5 alpha times t squared. Plug in my variables, go ahead and simplify, and I find out that theta final is equal to 150 radians. That's not my final answer though. It asks for how many rotations the sphere has made. Well, I know that one rotation is equivalent to 2 pi radians. So in order to solve for it, I'm going to take 150 radians, multiply that by one rotation, and divide by 2 pi. That's going to cancel out radians, and that's going to give me 23.87 rotations, meaning that this basketball rotated 23.87 times during that 20-second interval as it came to rest. Let's take a look at another example problem here. So this problem says a figure skater is spinning with an angular velocity of positive 15 radians per second. They then come to a stop over a brief period of time. During this time, their angular displacement is positive 5.1 radians. Determine their average angular acceleration and the time during which they come to rest. So let's list our variables like we had before. So initial theta is 0 radians because they're just starting at 0 degrees. Their theta final is 5.1 radians. Their omega initial is equal to 15 radians per second. That's their initial rotational speed, which was given to us in the problem. Their final omega is 0 because they're coming to a stop. Their alpha is unknown, and then their time is also unknown. So looking at our variables, we're going to have to solve for alpha first because time is in two equations, but the two equations that it's in, we're missing two other variables. So we're going to go ahead and use Shaggy Cat to solve for alpha. We're going to plug in our variables here. We're going to go ahead and simplify, and we get negative 225 is equal to 10.2 times alpha, and solve for alpha by dividing negative 225 by 10.2, and I find out that alpha should be about negative 22.06 radians per second squared. Now that I have alpha, I can use that to go ahead and solve for time. I'm going to use little pup to solve for time. Go ahead and plug in my variables, manipulate the equation a little bit, and find out that time should be equal to 0.68 seconds, meaning that this person comes to a stop pretty quickly. So we've talked about rotational, and we talked a little bit about translational quantities, the ones that we're used to, but I want to see how they're related to each other when it comes to rotational kinematics. So in this example, we have a merry-go-round down below, where Bonnie is sitting on the outer edge of the merry-go-round, and Clyde is sitting midway between the center and the rim. The merry-go-round is going to make one complete rotation every 2 seconds. So right now we see it going around. So we have 2 questions off to the side. Clyde's angular velocity is the same as Bonnie's, twice Bonnie's, half Bonnie's. So if we think about this in terms of omega is equal to delta theta over t, well, when they do one complete rotation, their delta theta is both the same. They're both going around the exact same angle, and their time is also the same. Therefore, their omega, or the rate at which the object is spinning, is the same in this case. So Clyde's angular velocity is the same as Bonnie's. But what about their tangential velocity? Is Clyde's the same, twice, or half? When relating rotational and translational quantities, we know that omega times the radius is equal to the velocity, and we'll talk more about this on the next slide. But we know that Bonnie's radius is greater than Clyde's radius, and therefore Bonnie's velocity would be greater than Clyde's velocity. Since Clyde's radius is half that of Bonnie's radius, that means that Clyde's velocity is half the velocity of Bonnie's velocity. Therefore, Clyde's tangential velocity is half Bonnie's velocity. We can see that Bonnie is traveling more tangentially than Clyde is, because she's going around the outside of this merry-go-round, where Clyde is going around the inside of this merry-go-round. They both are taking the same amount of time to make this rotation, but since Bonnie's covering more distance, she has to be moving faster than Clyde. How much faster is she moving? Well, Bonnie's moving twice the speed that Clyde's moving, therefore Clyde's velocity is half that of Bonnie's. So let's compare these rotational and translational quantities a little bit further. We know that the radius of rotation can be used to convert between rotation and translational quantities. I'm going to show you down below. So distance in rotational is theta. In translational, it's d. And the relationship between the two is just theta is equal to d over r. Velocity is going to be very similar, where omega in rotational is equal to v over r in translational. And then lastly, acceleration. Alpha is going to be equal to acceleration divided by radius. Let's take a look at another example problem, because we can never have too many. A tire has a radius of 0.33 meters and its center moves forward with a linear speed of 15 meters per second. We want to figure out what the omega of the wheel is. And we also want to figure out what the tangential velocity of a spider holding on at 0.175 meters from the center is. So if we look up above, we're actually given our variables in translational quantities. We're given meters and we're given meters per second. So we know from the last slide that distance can be related by saying that theta is equal to d over r and velocity with omega equal v over r. So if we use that equation, we can plug in our variables and see that velocity is equal to 15 and the radius is 0.33. So I just plug in 15, divide by 0.33, and I find out that omega, or the angular velocity, is equal to 45.45 radians per second. Now that I have the angular velocity, I can use that to solve for the tangential velocity at certain distances. I'm going to use the same equation. So I have v is equal to omega times r. All I did was multiply the r over to the other side. I plug in my variables, and I find out that the velocity at 0.175 meters is actually 7.96 meters per second, which makes sense because its tarantula is closer to the center, so we would expect it to have a smaller translational velocity. Just like Clyde had a smaller velocity than Bonnie because he was closer to the center of the merry-go-round. Alright guys, let's take a look at example number 4. So in this example, we have a rope that is wrapped around a wheel with a radius of 0.4 meters, and it's going to start at rest. The rope is pulled with a constant acceleration of 4 meters per second squared. Note that it's a constant linear acceleration. We want to figure out what is the angular velocity of the wheel after 10 seconds. Well, if we recall from before our rotational and translational and the relationship between them, we can use these to help us out. So first, we're going to go ahead and convert A into alpha. So the acceleration is 4 meters per second squared, and the radius is 0.4 meters. So to convert that, we're just going to do A divided by R, and that's going to give us an alpha of 10 radians per second squared. Next, we're going to go ahead and figure out the angular velocity. To do that, we're going to use our equation little pup, where we know that omega final is equal to omega initial plus alpha times t. Omega final is what we're solving for because it's asking us how fast it's spinning after 10 seconds. So we're going to go ahead and plug in 10 for our time and 10 for our alpha. We find out that the omega final, or the angular velocity after 10 seconds, is 100 radians per second. So let's just quickly recap everything that we talked about, and mostly the relationships between translational and rotational variables. So in translational, we have position, which we would say is the location of an object with respect to the origin. In rotational, that's the angle, and that's the rotational location of an object with respect to a coordinate system. So still the location of an object, it's just one is a linear location, while the other is a rotational location. Displacement is the change in position, and the angular displacement is the change in the angle. So both very similar here. So we know velocity, or sometimes we call it speed, just meaning the magnitude of velocity, is the rate of displacement, or how fast an object's moving. For rotational variables, the angular velocity is the rate at which the object spins, or how quickly the object is spinning. Acceleration is the rate of change of velocity. So acceleration is how quickly we're changing our velocity. And for rotational, angular acceleration is the rate of change of angular velocity. So how quickly are we changing the rate at which we're spinning? Are we speeding up the spin? Are we slowing down the spin? And that does it for us, guys. We are done with our rotational introduction notes. So just make sure that when you're solving problems, you're always listing and identifying your variables, because that's going to help you out, because it is a little confusing using these new variables. But when we list them out and have our equations in front of us, it's easy to find which one to use.